All right, here we're on chapter 1, ingredients of change, functions and limits. So this is section 1.10, logistic functions and models. All right, so exponential growth with constraints is kind of what this is going to be called. And this is common in the spread of disease, the spread of information, the marketing of a new product, the adoption of new technology, growth of certain populations. It's going to be a different kind of mathematical function. And it's called the logistic function, and that can be expressed in this formula here. So f of x equals our L divided by the 1 plus a e to the negative bx. So it's got an exponent in it, and we have this a times it, and L, A, and B, so the A and B and the L on top, they're all non-zero constants, because if any of those were zero, then basically we get rid of, here, if that was zero, we get rid of this whole thing, we just have L over 1. If this is zero, we get 0, and if that's 0, we just have 1 plus a. We don't have the exponential part. So all of them have to be non-zero. And then the number appearing in the numerator of a logistic equation determines the horizontal asymptote y equals L, so that's one of them. And usually the other one is going to be set to y equals 0 or as close to possible, and so it's going to be down at the other end, okay? Now, scatter plots are very useful when deciding whether or not to use the logistic model, and you'll see why here in a second. And it's because your scatter plot's going to have like that S curve here, or like sort of like a 2 here, kind of backwards a little bit, but it doesn't go out far enough. But that's the kind of curves we're looking at. So again, we've already saw, the logistic model is this, A and B are non-zero. And in this case, L has to be 0 is the limiting value of the function, okay? And again, remember we said that was this upper horizontal asymptote up here. And it has to be greater than 0 because usually 0 is the one up here. So it's going to be somewhere up here. So it might be really short. It might be, 0.1, but it's going to be up there. Now the logistic function of f increases if b is positive. So b is greater than 0. We're going to get the S curve. And it's going to decrease or have this kind of almost a 2-shaped curve if b is less than 0. Okay. And again, we have the L, the horizontal line is going to be asymptote. And usually the x-axis is going to be one of the asymptotes too, but not always, but that's usually where we try to make it. And so we're going to have to shift our data so it gets to that point. All right, what is the behavior of it? Well, if we just look here, the behavior of this, well, as we go to positive infinity, it goes to what? L. It goes all the way out to L, whatever L is. And as it goes to negative infinity, well, it goes out here to, 0, because that, again, it's trying to get close to that x-axis, so it's going to get very close to 0. And so as it goes to negative infinity, goes to 0, goes to positive infinity, that goes to L for the increasing logistic function where our b is greater than 0. Now, if our b is less than 0 and it's a decreasing function, what happens? Well, then as we go to negative infinity, we're actually going to L this time, and so that's going to be our limit. And the other one is we're going down, and it's going to be going to 0 on this side. So as we go to positive infinity, our limit's going to be 0. So another thing to note is both increasing and decreasing forms have a single inflection point. And so that's where it changes from increasing to decreasing or decreasing to increasing. And so it's going to be about, right about here. And as we can see, it's concave up here, and then it switches to concave down. Now this one, it's going to be, somewhere about here. So it starts out concave down, and then it ends up concave up, okay? And that single inflection point, we can actually find that really nicely with our calculator, with something we're gonna learn about later in the course. So again, we want to align input data shifts horizontally. So we want to go left to right usually. And it's often advantageous to align the input data so the values are close to 0 before fitting a logistic model. And that's kind of the key. We really want it close to 0. And such an alignment might avoid extremely small values for the coefficient of the exponential term in the logistic function. But it's also very possible to shift exponential and logistic models vertically by realigning the output data. So such an alignment would change the lower lowering the limit values from 0 to some other number. And we do this occasionally when a shift is going to significantly improve the in behavior fit, or there's a reason to believe that the data approach a different limiting position where the input axis really is at. So we can do it, and when you get to real life, you'll have more experience and you'll be able to do it easier. But for the book, it really kind of tells you, okay, align this way. And when we see a year, we already line to 0, unless instead of saying that first year they give us, we put to 0, they say maybe 5 years before that was 0. So then our log model would fit or something. So there's key little nuances that we kind of have to take into account when we're doing these. All right, so I'm going to pause there and come back in a little bit.